Every electrode manufacturer will recommend the travel speed and current and voltage. Our intention is to keep the current and voltage and the travel speed in the most optimum level so that we can give maximum deposit. See, manual metal arc welding or shielded metal arc welding is a slow welding process, and it needs a lot of cleaning, a lot of personal skill of the welders, because it's like an art. You and I, most of the engineers, I know welding quite well, but I will not be able to do an inch of welding because I don't have that skill. So welding skill is a very special skill to be developed and to be practiced continuously. If a welder does not weld for 6 months, he or she will lose the qualification. ASME requires the welder qualification to be repeated every 6 months. Now, this can be done by repeated good work. If the welder, after initial approval, is continuously working and his or her performance is good based on the ongoing work, so they can be continuously renewed, but every 6 months they have to do this. This is because the welder, if they are not welding, will lose that skill. So coming back to that, what is better, to do fast welding or slow? No, you have to go exactly with the specified limit that WPS, welding procedure specification, specifies. Now our intention is to go at the higher level of the speed, because more speed and little more current and voltage combination, you can achieve higher weld deposit. That's what we need for economics of welding, because ultimately that welding process has to be cost effective. Now, our intention is to go to the higher level of the speed and deposit. So as you start increasing the speed, which is our intention, at some speed, which is called critical speed, beyond certain speed, you cannot exceed. You cannot go beyond certain speed of welding. Why? Just imagine when the welder is depositing the weld. Here what is happening? The weld pull is here, and there's so much of mass of the material. So they drain out the heat. So very fast cooling forms martensite, that you know. It gives like a quenching effect. So if you are doing rapid cooling like quenching or very fast cooling, martensite will form, which is a very hard microstructure. That's not desirable because this can also give higher brittleness. So weld can become more fragile in nature. So we don't want high amount of martensite to form. So if you are welding at a faster speed, heat input is even less, because Vi by Vs gives you arc energy into coefficient of thermal transfer gives you the heat input. If the denominator is more, the Vs is more, the travel speed is more, so you have got effectively less heat here. So you have got less heat because you are traveling so fast, and the quenching is also happening because there's a huge amount of mass to drain out this heat or absorb the heat. So you are actually accelerating the quenching process. So with the speed increasing, martensite will form, harder microstructural form, which is not desirable. So we would like to achieve a speed which is highest and the best, which meets the requirement of hardness, tensile, yield point. They can be bent. We perform bend test for the procedure qualification, and also ability to absorb impact, where we do Charpy impact test. So intention is to increase the speed, but there will be limiting speed below which it is safer, above which more martensite will form and the weld becomes more harder and more fragile. This is the reason welding speed is limited. You cannot exceed and do very fast welding where you are doing more harm. You can give more deposit, but you are depositing faulty deposit. So how we achieve the critical speed beyond which you cannot go? So as I said, our intention is to increase the speed at an optimum level and qualify in the procedure. Once the maximum speed that you can reach, yet get the desired property, that's the point we want to achieve by welding procedure specification. So how do we actually calculate the critical speed beyond which you cannot go? Very simple process. For example, you have a plate and you are performing weld, say at whatever speed, and then take a hardness survey. See what is the value. And always there is a maximum hardness specified for the material. It could be 185, 200 BHN or whatever is given as per the specification. You don't have to remember, memorize. Look at the standard. So once you have performed, see what is the hardness value. Then increase the speed again, keeping all other parameters. Now you are giving higher deposit at a higher speed. Again check the hardness. See whether it is still acceptable. At some point you find this is approaching the maximum hardness value, beyond which it will exceed the hardness that is allowed by the standard for this particular material, because you have to check hardness of the deposit in the HAZ, which is called heat affected zone, as well as the parent metal. With parent metal, there is not going to be much of a change. The changes will be in the deposit as well as in the heat affected zone, which is adjacent to the weld deposit, 4 or 5 millimeter area, which is beyond the weld line, and that goes on the parent metal side. That's the heat affected zone, the area affected by the heat during the welding. So you have to take hardness reading in the center of the weld sample. This was cut from a spiral welded pipe, and this was the pipe thickness. So here what we do, this is the weld, and you can see some area which is clear, heat affected zone. There is a very shadowy line. So this is a heat affected zone. This is the weld deposit. This was done from both sides. There is the inside of the pipe, that was the outside. The surface is very nice finish, done with submerged arc welding process both sides. So after that it is cut and polished, and here on the weld we are going to take hardness sample. On the heat affected zone we do micro etching, we do etching, and then the surface will be very clear, the weld will be very clearly defined. So on the weld, we take hardness sample. On the heat affected zone, we take sample. And on the parent metal, also we take the sample. And we compare with the requirement. If at the highest speed that you want to achieve, which is the best level of speed to achieve, and still you have got the hardness and other values, mechanical property, elongation, and then impact, all are fine. That's what is the speed that you have established and validated in the procedure, and that's the speed maximum you can go. That's how we achieve the critical speed of welding.